this code. Okay, sure. Okay, sir. Yeah, so this particular code will randomly pick endpoints from a uniform PDF, from a one-dimensional uniform PDF. The number of points that we chose here are 20. You can always change its value, and we are drawing endpoints at random on a line from -4 to 4. Okay, and the way you pick endpoints at random is you start with the you start with the random generator. RAND, it does the job of picking n values because 1 by n is so even before that. Rand of 1 comma n, the job of uh, sorry, sir. Okay. Maybe I'll try to.
Can you go to view? Yeah, view. There'll be a zoom in. Can you say there's a zoom in there? Just press that a couple of times. This is super. This is good. Is this good?
Okay. That's good. Okay. Is this good now? Okay.
Yes.
Yeah. Okay, so thank you. Yeah. So let me repeat that in case anyone among you have missed it. So we start with a value n as 20. So we are trying to pick 20 points at random from a uniform PDF, and we define the line. We are trying to pick the points on a line whose length is 8. That is, it is from -4 to 4. Yeah. So the way we generate these endpoints at random from a uniform PDF is given by this line 11. I'll now explain how what exactly this does. Okay, the rand function, in general the rand function, it tries to pick 1 by n size of elements from a uniform distribution between 0, 1. Okay, so the job of rand of 1, n is to pick randomly distributed point from a uniform PDF 0, 1. Since we want the distribution from -4 to 4, we will try to scale it to 8, as in Okay, then it is fine. Yeah. So the way the multiplication factor b minus c ensures that correct. Yeah, that's it. So yeah, so once we when we run this, okay. So what you see here is a realization of points, 20 points drawn from a uniform PDF. The next slide in the presentation, it asks you to do this in 2D. As in, so till now we have seen how to draw points from a 1D from a one-dimensional line, right? So this asks you to do it in a two-dimensional line. You can take a screenshot of this and try later, but it is same as what we have seen in 1D, except that you have to draw from a two-dimensional plane. As in, x should be drawn from -5 to 5, some 20 points from -5 to 5, and 20 points from on the y-axis. So that's how you get the IID uniform distributed points drawn at random.
I want to add one small point here. So changing it to rectangle is easy, but I think if participants want to understand how these forms are also deployed, maybe something like a disk is also very useful.
Yeah.
So the A, they can choose whatever they want. It can be in 2 dimension or 3 dimension, right?
Correct.
So they can do the same thing for 2 and 3 dimensions to model a swarm.
Right. So the way you do that the way you do it is you will have this theta, which captures the angle at which the point is located, that is uniformly distributed, and you will have the radius. Suppose if it is a 2D disk, you will have a radius proportional to square root of uniform. That's a basic concept that is there in the probability theory. You can go through that and try to generate points using this concept. Okay. Um, so till now we have seen what has happened in 1D and 2D. The 3D case can be seen as just a stack of 2D disks. For example, uh, if you imagine a 3D, if you imagine drones present in air, they can be realized using some n number of disks, wherein in each disk you generate some few points according to uniform PDF. So this is what we call as uniform binomial point process in 3D. Okay. It's just like stitching the 2D disks to get a 3D cylinder or a 3D pattern in space. So in the literature, there are a lot of works who try to model UAV locations using this binomial point process in a cylinder, or who try to model the swarm locations of who try to model the swarm of UAVs using the models that we have discussed before. Um, you can go through this papers and see how they have how they have used these models to generate some insights. Uh, so in the upcoming slides, we'll see what if n is random. For example, in the previous slide, we fixed n to be some deterministic value, right? Now, what if n is some random variable? It can drawn from any distribution, for example, Poisson or uniform or geometric or binomial. Now, given that you have chosen a random n value, you can ask to place those n points uniformly and IID at random in the given tile. So this generates one kind of process. The reason why I am starting with this is we'll generalize this to something called something like having n drawn from Poisson PMF from in all the tiles. So if you recall the slides presented by Professor Sundar, you can see you can see that or else. Okay, let me not go there. But the main takeaway that I want you to take here is, in each tile you have a different intensity of points. So all these different intensities in a given area would result in a point process, something called inhomogeneous point process. The reason why it is called inhomogeneous is if you look at the area this area from 4 to 8 and 0 to 4, although both the tiles have equal areas, the intensity in each of these tiles is different, causing it to not have a homogeneous process. If we make sure that if we make sure that the average number of points in each tile is proportional to the area, that's when we end up having a homogeneous point process. This was already discussed in the previous in the first part of the course, so I'm not going very much in detail. You can go through the MATLAB codes which demonstrate how dividing each rectangular tile into further smaller grids would end up having again a separate PPP of the same intensity.
So I have one point that I want to mention here to kind of chime in with what Taiba said. If you see on slide number 14, that is what she's showing now. Okay, so you see this is like on the left, there are two plots that you see. On the left, there is basically a point process where you have lambda, which is 10, and one of them is 50. Is it everything is 10?
Yeah, everything is 10. So.
Okay, so that labeling, okay. So what you can see here is that you can kind of intuitively at least get a feel that you are getting a different collection of random points as you move from one tile to the other, correct? They look quote unquote similar in the sense that they look similarly random. There's no specific pattern in each of them, right? So, and if you see the same thing, it is being played out when you look at the 16 subdivided grids, right? So this actually goes back to this idea about ergodicity that we discussed, right? So what is happening is, because this is an ergodic process, okay, your your ability to actually find certain averages, okay, and find the average over all the tiles, okay, is sort of bolstered because the process itself seems to be kind of creating, quote unquote, a new version of itself every time, right? So that you don't need to have separate realizations to get your average. Okay, so that's one point that is kind of showing up here. Right? Yeah, please.
Yeah.
Need to see carefully both the pictures,
Yes.
the points.
Yes.
The points are stationary, and the divisions have been made 4 to 16.
Yes. Yes.
Is it right, sir?
Yes, correct.
Both the pictures have same locations
Yes,
of
yes,
the
they're
points.
the same. They're the same. You're right.
Yeah, yeah. Okay.
Good observation.
Oh,
Yeah.
thank you, sir.
Yes, yes, yes. The only thing is, I think what she's trying to show here is that she was trying to show homogeneity. I was kind of adding another context to it, saying that, you can even notice, you can get a feel for why it is ergodic.
Yeah.
Right? You're kind of
true,
seeing
sir.
different copies of that small tile, right? Different versions of that small tile show up in different of all these smaller tiles.
Yes,
right?
sir.
So the first tile, second tile. So what is happening is you can take the average of all of them without waiting for another realization of the PPP.
Right, sir. Ensembled average if you have to take.
Yes. So that just like, for example, if you take a stochastic process in time, you can just average out.
So these have been simulated for how many runs, sir? 10,000 or more than that, sir?
This is a single realization.
Single rail, but
Yes.
if I run it again, it will come different?
Yeah.
Yes, it will become different.
So,
Exactly.
but you have not tried it by ensembling, averaging over 10,000 time or something?
So if I ensemble average,
Yeah.
I cannot show you something like this.
Okay. Then
Right?
it will be
Because-
stationary, sir, almost?
No, if I do any averaging like that, I'll get a single number out.
Only single number we get. Yeah, that's
I have to say something about the average, right? I think the main motivation that she is done, what we're doing here is that we are trying to show homogeneity. So if you see the first thing, different tiles, the point process looks very similar.
okay.
There's not something particularly different between the two.
Yeah,
Right.
there is no particular difference.
There is
Right.
no pattern present.
Okay,
Right.
yes, sir. Thank
And
you.
another thing is, it is almost as if, somebody took, one tile of the point process,
Yeah.
and the next tile is basically some
Guesswork
other
can be
version.
done. Based on that, we can do the guesswork. Okay.
So that homogeneity and ergodicity are coming in like this, very, very naturally in this case, is
Yes,
what
sir,
I'm saying.
that is clear from this. Okay, sir. Thank
Yes,
you.
yes, yeah.
So, yeah, this is again when you divide it into 64 subgrids, you again see the same intensity in each of the grids, showing that the process is homogeneous. And this definition has already been introduced in the previous slides, so I'm skipping it for now. And if you see some real life examples, suppose you have a coffee cup and you're trying to sprinkling the coffee powder at some height, and what you see is a uniformly distributed powder on the cup. For example, if you look at the cake example also, if you take some randomly picked number of choco chips, if you sprinkle it uniformly at random, what you get is a Poisson point process. So both these examples can be seen as some real life examples for PPPs. Now that we have seen how it is in 2D, if we want to model UAVs in 3D, for example, in the binomial point process case, we have seen that we have modeled each layer as some disk, and on each disk we have picked points at uniformly at random. Similarly, if you want a 3D PPP in space, what you can do is you can divide the space into some planes or even disks here, and you can fill each plane or each disk with Poisson distributed number of points, which are picked uniformly at random. So this is just a demonstrate the reason why the intensity goes down as we go high is very much tied in with the real life modeling of UAVs. For example, if you want to deploy UAVs in 3D, you would not want to have UAVs too high because you want to avoid the large scale path loss efficiently. If the UAV is placed somewhere here, it is very much possible that it will experience very high large scale path loss, resulting in a decreased performance. So you can always model the intensity of the point process such that as the height goes up, the number of points present on the higher heights are lesser. So this is one way of modeling a 3D PPP. You can always have equal intensity on all the planes, but that is one model. That is one way of modeling, and this is one way of modeling it. Many different kinds of models are in use in the literature. Few among them we have mentioned here. One is a Poisson cluster process, and the other is a Poisson line process. We'll start with what a Poisson cluster process is. Suppose that there are a collection of base stations who are trying to serve the UAVs present in air, and even before that, let me formally introduce you what a Poisson cluster process is. A Poisson cluster process is something where you have the parent UAVs which are present which are blue in color, which are marked blue in color, are distributed according to a PPP, and you have child UAVs around each parent UAV distributed uniformly or in a Gaussian or using a Gaussian model. Any model, you can choose any model for that matter. Depending on what model you choose for the child UAVs, you will get a different kind of cluster process. So in this particular example, we have chosen them to be uniformly distributed in the 3D space. So this is what we call as Poisson cluster process. So using this model, what people have done in the literature is they would study what is the performance seen at a UAV, assuming that all the UAVs are being served by this base station. So this is one mathematical model people use. And one thing I would want to highlight here is it is not necessary that there is always a parent UAV in each cluster. You can as well note it as some reference point around which the child UAVs are distributed in a disk, in a cylinder, or in a sphere, or in any rectangular grid. So it is not necessary that you have a parent UAV in each cluster. And also, in real life, when you want to model this close to the real life examples, you would want to induce some repulsion between the clusters, because you do not it is not efficient to have two clusters at the same point doing the same job, right? So we would want to introduce some kind of repulsion between the clusters so that no two clusters overlap. So this is one kind of model. The other model is the Poisson line process. So if I don't know how many of you have seen this, but there is a recent ad by Swiggy Instamart wherein the drones try to deliver the products or the okay. So they try to deliver the products or the goods to the specified location. So it's a similar example wherein there is a warehouse which is trying to deliver goods to some areas in the city, and the UAVs are following some specified path or along in the 3D space. For example, you can see you can view them as aerial highways, as in you have some predefined paths over which the UAVs should travel, and all these UAVs are being served by the base stations on ground. When I say they are being served, they are being controlled. They will communicate with the base station. Maybe they will send their coordinates, or maybe they will tell their status, or maybe they will share their speed. Okay, all these are kinds of data that will be exchanged between these base stations and the UAVs. So this communication network, given this communication network, people would want to study the performance of the installed UAV. So this can be modeled using a process called Poisson line process, wherein we pick Poisson number of lines. Here I have aligned them horizontally and vertically to essentially map it to the example that I'm showing here. But in general, it is not necessary that they are only horizontal and vertical. They can be randomly oriented. Okay, and given each line, you randomly sample UAVs from a Poisson process. That's how we end up having a Poisson line process. I'll briefly walk you through the code for both the Poisson cluster process and the line process. So I'm talking about. So I'm talking about this process.
Again, can you make the MATLAB code bigger when you're presenting?
Yeah, I'll do that. So.
Yeah.
So we are now seeing how to obtain this model in MATLAB. Is this sufficient? Hello, sir.
It is okay with me. Is it okay, Professor Saipat?
Hello.
Okay, great, perfect.
Okay.
Yeah.
Yeah. So on screen so that you can show it better. No, it's not allowing me to do that. Okay. So the lambda base station here corresponds to the base station point process intensity, and lambda UAV corresponds to the parent process intensity. All the UAVs in the blue are the parent UAVs. So the intensity is given by lambda UAV, and the child UAVs have an intensity of 5, which means they are on an average 5 number of UAVs per parent UAV. So we can determine the cluster radius, cluster height, parent height. All these are the parameters that we can tune.
So one small correction. Yeah. Lambda UAV is 5. Lambda child is 5. Means that the mean number of children per UAV is 5 multiplied by the volume of that.
Volume of that.
So that's pi times 2 square times 1.
Right.
Yeah. Yes. So one more point worth mentioning. I don't know whether you already mentioned it.
Okay.
In this case, the parent, the blue dots, which is the parent sort of points, may or may not actually have a UAV there.
Yeah, I have mentioned that.
You mentioned that. Okay. Yeah, I think that should be. It's a very important, subtle point, right?
Yeah. So it is not necessary that we always have a parent UAV. It can be some reference point around which the child UAVs are distributed.
Yes.
Yeah. So the way we generate PPP for ground-based, so this is a general way to generate PPP. We first pick n. We saw that n is random, right? So n is random. Is given by lambda times the area in which we are trying to generate. So area is given by 20. So it's a square area. So area size square gives you the Lebesgue measure of that plane that we are looking at, and lambda base station is the intensity. So given this mean, you will first generate the number of base stations, which is a Poisson distributed random variable. Once you have that, we generate that many number of points uniformly at random. Okay. And since the base stations are assumed at 0 height, we have along the z-axis we have zeros. Similarly, we follow the same code to generate the parent UAVs. And once you have parent UAVs, you can generate child UAVs using any model that you want. For example, here we have generated them uniformly at random. You can as well generate the child UAVs according to some 3D Gaussian process. Meaning, you can have you can have child UAVs closer at the center and very sparse along the edges of the cylinder. Okay, that's one way of modeling. We will call that Martin core process. We'll not get into that, but I'm just trying to tell you that there are different kinds of cluster processes. Okay, here again, given each parent, for I equal to 1 to number of parents, we are trying to generate the child UAVs according to Poisson random variable. So here, if you see, we are trying to place the UAVs on a disk. That is where you see that theta is uniformly randomly distributed, but r is square root of uniform multiplied by the radius that we have. So this is what I was mentioning when I said the points are uniformly distributed on a disk or a sphere of a given radius. And the rest is all just plotting the obtained points using the scatter plots. So this can be understood. This is how you generate a Poisson cluster process. When you see a Poisson line process is something that I mentioned here. Yeah. So this is what I'm referring to right now, a Poisson line process.
You need to zoom it, please. I can't read it.
No, I have already presented it, sir.
Is it? Okay, okay. Sorry. Maybe my eyesight is bad. Yeah.
No, this I have already presented. I did not most to them. So I'm
okay. Sounds good. Okay. That's
yeah. So this is the, we'll see how this was generated now. Okay.
So just to give some context here.
So as I said, a Poisson line process is something where you generate first Poisson.
Your voice is cut out. I don't know if it's an issue with my network or did everyone see this issue? Oh, I see. No. I think the problem is I could not hear Taiba's voice very well. It cut out. I was wondering whether it's just me or...
Is it better now, sir?
Yes, it's better now. Yeah. Yeah.
I'm meant to present it, sir.
Yeah. Please carry on.
Yeah, so you were mentioning something. You wanted to add something to this?
Yeah. As Professor Kamesh said, see, these line processes are a way to impose structure on the UAV traffic. Correct. So instead of saying that UAVs can travel wherever they want, whenever they want, we impose certain regions where they can exist. And conversely, if someone uses things like the whole process, you can also impose regions where they cannot exist.
Correct.
Right. So that's something that we're using this Poisson framework to define point process on objects which are not just a plane or a cylinder or a Borel set. We're trying to convert it into other things.
Right.
Just to give that context. Yeah.
So we'll see how this was generated. So as I mentioned previously, Poisson line process is something where you have Poisson number of lines oriented in the 3D space, and once you have a line, you have to generate the Poisson number of points on the each line. So here lambda L corresponds to the intensity of the lines, and lambda P corresponds to the intensity of UAV per line. So we have initiated this area size with 3, and we are assuming the height range is from 2 to 8. You can always here you are trying to generate a Poisson random variable, which is a Poisson number of lines, and once you have that, here these lines of code usually they what they are trying to do is they are generating either a horizontal line or a vertical line with a 50% probability. Since
Taiba, can you hear me?
am
I
I
think
audible,
professor
sir?
is trying. Yeah, the professor is trying to say
Yeah,
something.
yeah,
Yeah.
yeah. Eh, No, it has been completed. So I have shared the slides with you, right? They're already, yeah, they're already there in it. Yeah.
Yeah, you can share the.
Sure,
I
sure.
think the source
Yeah,
code can be shared. Yeah, yeah. Which one?
no, no,
Which
sure.
ones? Which ones are we referring to? Which ones are we referring to?
No, no, sir. You can share it.
Yeah. These are actually pretty standard codes. Yeah. So you can take them. I think yeah. So if the participants want to do it, then that will be even better. Yeah. That will also actually, Taiba, that will also help you. Sort of maybe if they're able to run it by themselves, they can review the code because all these comments are very standard comments. There's nothing special, right? So my suggestion is we can.
No, these are just the demo.
Actually, I don't know whether it's an issue with my network or network on that side. Okay, because you're able to hear me when I talk, no? Okay.
Shall I turn off my videos?
Yeah, maybe that's the issue.
Okay. Yeah, that's one.
There are few interruptions while you are presenting, ma'am. The screen is visible, but while presenting, there is an interruption.
No, I think the audio was getting cut out very often. I think that was the issue.
Yes.
I for a good part, I did not even follow what was happening because it was too much of, yeah.
Okay. Am I audible now, sir?
Yeah. Now I think your voice is clear, but slides we have to see.
Yeah. I'm able to present them.
Yeah, now it is good, ma'am.
Okay, thank you, sir. So shall I continue?
Yeah, continue, ma'am.
Okay. So till now we have seen different ways to model UAV point process. Different ways, as in the Poisson line process, or the cluster process, or the PPPs, or the BPPs. Now we'll see where exactly are these used to study the performance of a network. So these are actually a part of our work, which we have, these are the accepted works at Globecom and ICASP. I'll present them in a while, but before that, we'll briefly see different kinds of applications and different kinds of implications that we have in a UAV network. So yeah. So if you look at the figure on the left, here, a typical user is receiving service from both the ground base stations and the aerial base stations. Aerial base stations refer to the UAVs. So you can view this as a use case where we are trying to improve the performance of the seen at the typical user, given that there are some buildings on the ground, because of which these paths from the base stations are being blocked. In that case, you can ask for UAVs to provide the service to the user and improve the performance at the typical user. So that can be seen as one application where UAVs are used as aerial base stations. That is, having to have a line of sight link between the base station and the typical user, which is not usually seen on the ground base station to the user link. But having said that, it is not always true that UAV to the user link is line of sight. It can be non-line of sight too. I'll come to that in a while. The reason why the link between the UAV and the user can be non-line of sight is that there are some limitations given by FAA. There are some limits given by FAA. That is, you cannot deploy UAVs beyond certain height, say 400 feet. It is around some 120 or 130 meters. So, given that constraint of UAV height deployment, you can see that the UAV links between the links between the UAVs and the users on the ground are also blocked by the buildings, any tall buildings in the urban areas for that matter. So those links are also susceptible to blockages, especially when we are using millimeter waves for the communication. So if you use millimeter waves, they are more susceptible to absorption, right? So the link is instantaneously non-line of sight. But to model this feature also, as in to model whether the link is line of sight or non-line of sight, ITU has proposed a model wherein it's a probabilistic model which tells you based on the distance between the user height and the transmitter height, as a function of some parameters, it will give with some probability this link is line of sight, or with some probability this link is non-line of sight. So PL of delta R is that probability with which the link can be in line of sight. It is a function of many parameters like height of the transmitter, height of the difference between the heights, or lambda A and lambda B corresponds to the blockage density. Blockages as in the building densities, and lambda A corresponds to what is the ratio of building area to the total area. So it's a function of all these parameters. Once you have that probability, you can view it as some Bernoulli random variable with probability P. So suppose there is a link, UAV, suppose the link is between the UAV and the user on ground. If suppose that given all these parameters, you have a probability, say 0.5. So with 50% probability, the link is in line of sight, and with 50% probability, it is in non-line of sight. You can view it as a Bernoulli random variable with probability P. And this is a little mathematically more involved model, which leads to some interactability when you try to use this in the math. So one simple model people have been using is this ball model, wherein
Saiba, I think Professor Sai Prakash has a question.
Yeah,
Okay.
ma'am. Epsilon you have used, it is the environment or what, madam?
which one, sir?
Epsilon.
Epsilon, it is the average building height. I'm sorry, I
Average
forgot to
building height.
mention
Okay,
it here.
okay.
Yeah,
Right.
epsilon is the average building height in a given environment. Suppose, so there are values given for this epsilon,
that is
delta
okay.
R, lambda A and lambda B for
Okay.
each environment. If it is suburban, there are some set of values that are
No,
predefined.
there is a square root 2 epsilon delta, right?
Right.
The epsilon is
Epsilon is the average building height.
Okay.
So if we look here, I need to zoom
that is
in.
really constant.
Yeah, it's a constant given a particular environment.
Yeah, right.
If it is a rural area, epsilon will be very less. If it is an urban area, it will be high. That's how it is modeled.
Instead of that, why can't we use the Nakagami channel or what? When there is building height, the epsilon will go beyond 1 and above 1.
No, okay.
So I think, no, I think I'll let you answer. I have a slightly different point. I think I'll let you answer the professor's question first.
Okay. So I think the building density, the building height can be modeled with any random variable given the environment. That's what I think so.
Thank you, ma'am. That is.
No, I think Professor Sai Prakash Garu. So here is the thing, right? At least I want to give a slightly different, my understanding of this equation, correct? This, whenever at least I see a probability and a sum of some more terms, I tend to look at them as probabilities again. So probability of A multiplied probability of B and so on.
Yeah.
So basically what they are saying is something is line of sight only when everything in the path is line of sight. Even if there is one blockage, it cannot be line of sight.
Yeah,
correct?
that is true, sir. That's why I'm
Right?
saying that if it is
Exactly.
Nakagami cell, we can tune the parameter
Exactly.
either this way or that way.
Exactly. So what happens is this Nakagami parameter that you're talking about should be a function of the density of blockages, which is the density of buildings basically. Okay. And in some sense, a blockage to total area is something like the width of the buildings.
Yeah, that means that we should have a perfect channel feedback, which tells what the value of that.
No. There's no channel feedback necessary.
But
because
height,
as you
how
know,
we'll know that height and all?
No, height is known, sir. Height is known because the height comes from
the receiver. Okay.
So as you know, these UAVs have a IMU.
Okay, I thought at the drone.
So they have IMU,
No, I thought it is at the drone. Okay, sir, that is fine.
So what I'm saying is this Nakagami parameter that you're talking about is a function of two things basically: the distance and the height. Okay, and the density of things that comes in between. So if the probability of line of sight is a probability that everything in between the height is below a certain point.
Yeah, that is.
Okay.
It tells us whether it is a dense urban or rural.
Exactly. So what happens is basically if all these terms 1 minus exp of this, those are all very small. That means exp of this is close to 1. Okay.
Right.
That means the let's say denominator, the numerator, for example, is close to 0. Then that means there's basically very little chance that it will be line of sight. Okay.
But as the range goes to 60 gigahertz, what happens, sir?
Yes. So that's an interesting point. All these things assume that we are in the not in the. I don't believe that this model is accurate enough for millimeter wave.
The object height is more than the lambda, then it will not.
Yes.
Get totally.
And the other problem is 60 gigahertz is that unlike let's say sub 6 gigahertz spectrum, 60 gigahertz there is no diffraction.
Yeah, no diffraction.
So therefore, it cannot even penetrate. I mean, there is a joke that if you have a millimeter wave connection between your mobile phone and TV, and you're watching a movie, even if your dog or your child comes in the middle, okay, the movie streaming is stopped.
That's what happening right now, sir. When a call comes in, we are running out instead of staying inside the house.
So that is why the millimeter wave propagation is actually very sensitive. And in fact, the second part is also there. The people are talking about terahertz.
Yeah.
So terahertz, it will have even more of an issue than
that's why we are limiting the size only to the room, only at the access point only.
Right. So this is a chance, I think, on a slightly different note, the future way in which we'll probably communicate will mean using different bands for different distances. So if you want, let us say, within a room, maybe you'll use terahertz.
That's what the new radio says.
Yes.
But we don't know how it goes.
Yes. Right. So that's probably how they'll do it.
Yeah.
Only thing with these cases is only time will tell whether there are use cases that use it. Yeah, that's a problem. Yeah.
Because back end they are pushing everything into fiber, so they are assuming that front end it can go.
Yes.
Right, sir. Thank you, sir. Thank you.
Yes, sure. Yeah.
Yeah. So one more point that I want to add here is this model assumes that independent of whether a user is blocked or not, the user behind it. Suppose that there are two users at this point and at this point. It does not assume that all the users beyond this point are all blocked, because it independently chooses whether a user is blocked or not, irrespective of whether a building is present in that region or not. So that is one drawback that we thought that is in this model. To mitigate that, people have used a different model which is more mathematically tractable, which is this ball model, wherein people say, see, if at all the links are within certain radius, say capital R here, all those links will be in line of sight, and everything after that will have non-line of sight. So all the users after this disk will experience non-line of sight with the UAV, and all the users within this disk will experience line of sight. So this is a fairly simple model to implement. I mean, in a mathematical sense, and to gain more insights. So given this, we'll start with the motivation to the work that we have done. If we look at the existing architecture, suppose LAN connected computers or the cellular network, we all know how we all know what on what protocols these are designed. For example, if you look at a cellular network, there are some handoff mechanisms when the user moves from one cell to another cell. They're all predefined. But when it comes to UAVs, if at all UAVs are viewed as some users in air, there are no design considerations which will tell you how should the ground network be designed such that we can best serve these UAVs. So this is a different perspective compared to what has already been done in this area. So in the existing literature, people have viewed UAVs as some elements which are providing service to the users on the ground. For example, if you look at this example, UAVs are acting as additional infrastructure in the air who are trying to improve the performance of the typical user. But we ask a slightly different question. What if UAVs themselves need service? What if they needs to be controlled, and what are some design considerations that need to be kept in mind? One very first question one may ask is how should the ground base station should be designed such that we see good performance in a UAV network. Uh, one two ways in which this differs is the kind of traffic that we see. For example, if you look at the ground users, the kind of traffic that you see is basically either the text images or the video images or some kind of not mission critical data. So it is not the data that you exchange is not critical. It's not time sensitive. You can wait for a second or so to receive the data. But when you look at UAVs as users, that is not the case. If at all UAV does not receive some data within some fraction amount, within some time, the mission may fail. Maybe the UAVs were on a mission where they want to, identify some object on the ground, and they have some time limit within which they should do that. If the UAVs cannot receive that data for whatsoever reason, the mission would fail. So these are the kinds of challenges that one would face if UAVs are used as users. In our work, we'll see how a network is designed and how different parameters in the system would affect the system performance. So our first work is on infrastructure design for large UAV networks. Here, we have assumed that the ground-based stations follow a Poisson point process, and the UAVs also form a Poisson point process. They are present at some height h, and we assume that everything is static here. Even the UAVs are just hovering in air; they are not moving, and there are two kinds of data that are being communicated. One from the ground base station to the air, to the UAV, that is ground to air link. The kind of traffic is what we call as C2 traffic. C2 traffic is a command and control traffic, which will give command data to the UAVs. Like for example, the base station may ask the UAV to move to the left, to move to the right, or any data that is mission critical. So when I say that data is mission critical, it is usually latency sensitive, as in you should be able to communicate that data within certain slots. Otherwise, you would see a mission failure. Similarly, on the air to ground link, that is from the UAV to the base station, there is this payload traffic which is throughput concerned, because some kind of data that UAVs transmit are the images or the videos that it has captured. For example, if you see the image here, the UAVs tried capturing the fire accident, or else the UAV here tried capturing the landslide here. It is trying to send the status to some nearby station, maybe a police station or a fire station. So this is a payload. This is what we call as payload traffic. So you want to send more amount of data. Right? That's why we call it a throughput concerned data. One thing that I want to highlight here is all this communication is being happened in the presence of interference. If you see carefully, the data received by the UAV, by this UAV, is the signals received at this UAV are being interfered by these red dotted line signals. So assuming that these both are all the base stations are using the same channel, we see interference at this UAV. We'll see how, in the presence of interference, this latency sensitive traffic and the throughput concerned traffic would get affected, and how both these parameters, the delay and the throughput, are a function of this base station density and the UAV density. So this is what I was mentioning. And one more thing I want to add here is the A to G traffic can also be C2 traffic. As in, the UAV might be trying to communicate its own coordinates to the base station, saying, "Hey, I'm here. So send me some help." So that might be a kind of latency sensitive data that it wants to transmit to the base station. So the air to ground data can be a combination of payload and C2 traffic, whereas ground to air would be purely C2. So these are some specifications given by 3GPP. If you see, the C2 traffic has a latency constraint of 50 milliseconds, as in within 50 milliseconds, one should be able to communicate the data to the UAV. And payload traffic has a data rate of 50 Mbps, so it should be able to transmit as much big file as possible. But if you see the data rate of the C2 traffic, it is very limited. Reason being, the packets that are transmitted on ground to air are usually of smaller size. They are very small packets which do not need very high data rates. Okay? So given this background, I'll now explain the metric delay that we have studied in this paper. Okay, so sir, I'm still audible, right? Hello?
Yes, you're audible. You're audible.
Yeah.
Go ahead.
Okay. So this is one of the metrics that we have studied in this paper. We call it the mean packet reception delay. If you recall the concepts, and even before that, and even before that, here we assume that each UAV communicates with its nearest base station, as in it receives a C2 traffic from the nearest or the strongest base station. Okay, so that is the reason why I have mentioned it as nearest base station here. So in time slot number 1, suppose the associated base station is trying to send a C2 packet to the UAV. Due to the reasons that were mentioned in the first slide of this talk, that is the fading or the shadowing, it is possible that the UAV may not decode the packet correctly. So it may fail to decode the packet, and it will send the negative acknowledgement in that case. Then the base station associated with this UAV will try to resend the packet in the next slot. So again, given the randomness in the environment, given the channel conditions, the packet may not be successfully received at the UAV. It will again send a negative acknowledgement. Then the nearest base station would again resend the data. So this time, maybe everything was good, the channel was good, and it got to successfully receive the data. So these number of slots, these 3 slots, are what we call as reception delay. Okay. We call it the delay in receiving the packet successfully. That's how it is called, the reception delay. Now, you might ask, what is that one metric based on which the successful packet reception, or you may ask, what is that one event based on which packet reception or packet failure is decided? That is the signal to interference ratio being greater than some threshold theta. If at all in the first slot, if the UAV sees that the signal to interference ratio is greater than theta, it would declare that it has successfully received the packet. Else, it would say, I did not receive the packet, so it sends a negative acknowledgement. So if you see the event here, this would have been S by I less than theta. That is why it couldn't decode the packet. In the second slot also, it would have been S by I less than theta. That's the reason UAV could not decode the packet. In the third slot, it was able to decode the packet successfully, which means S by I here was greater than theta. So if you try to recall your concepts from probability theory, it is something like you see a success after some n failures, right? You saw a failure here, you saw a failure here, and this is the first time you saw the success. So this corresponds to geometric random variable. If you recall the concepts from your basic probability theory, this is the first time you saw the success. I mean, this is the first time you saw successful packet reception. So this random variable, the reception delay, is a geometric random variable. What we are studying here is a mean of that reception delay. When I say mean of reception delay, there are different sources of randomness, right? If you recall from today's course only, in the second or the third slide, we were discussing what should be the expectation upon. It should be on the fading gains, because there is the source of randomness comes from the g factor that was present in the path loss, or even the distances, because if you remember, there was a text in the red, can d be random, even d can be random, that is one source of randomness. All these randomness accounts to having a uh, randomness. All these sources of randomness will tell you whether the packet will all these sources of randomness will not let you decide on your own whether the packet is successfully received or not. Okay, so the main metric that we are going to calculate here is the mean delay. But if you recall the ergodicity property from the first part of the course, that's what we will be using in the current work. The actual metric that we are interested in is a spatially average delay, as in, suppose that each UAV has a nearest base station associated to it, and each UAV receives some data packets from its ground base station, and each link there might be some amount of delay. Say the delay on this link is some 10 slots, so the delay on this link is some 2 slots, 5, 6, 7, 8, so on. Okay, the average amount of delay is what we are interested in. So it is like sum of the delays on each links by total number of links is what we are interested in. Okay, but uh, evaluating this spatially average delay is same as finding the ensemble average delay from the ergodicity of the point process. So we will use that property to find the mean delay, and the other property that we use here is the stationarity of the PPP, as in, we will say that the UAV of interest is located at the origin but at some height h. So stationarity does not change the distribution of the process if you change the origin, right? So we will assume that there is some UAV present at the origin but at a height h, and we will study the performance of this link where this blue triangle is the nearest base station of this red UAV. Okay, and there is one more thing called the called Slivniak's theorem. What it basically says is, uh, conditioned on this point, the rest of the process has same distribution as the original process. So if you look at the let me go back to that slide quickly. If you look at the workout example in the beginning, there was this example that was given, right? Conditioned on a point at origin, I'm asking you what is the probability that there is a point at -1, 1. So a simple form of um Slivniak's theorem is that this probability is equal to probability that there is a point at -1, 1. So the distribution is same. So that's what the main gist is in the Slivniak's theorem. We will use that in the derivation. So it's like your independence property in the probability theory. So the system model, I've already described it.
I just want to add one small context here.
Okay.
So this Slivniak's theorem is a direct consequence of the memorylessness property of the PPP.
Correct.
So if you remember the previous talk, we talked about 3 properties, right? One is the memorylessness, the second one is stationarity and isotropic, which is motion invariance, and the third one was ergodicity. So we are using memorylessness, we are using stationarity, and we are also using ergodicity. All of them are being used in this case, right? All these properties are being used implicitly to derive what is the average time that a base station needs to connect it to its serving UAV.
Okay.
Correct? So if the base station needs a lot of time, it means that the network design needs to be sort of redesigned rather to ensure that you have a much faster connectivity. So we're measuring latency, in other words. Okay. Yeah, I hope that aspect of it is cleared up. Okay. So yeah, how much time do we have, Professor Sai Prakash?
Actually, before that, is there this theorem tells something like bounds on the parameters?
Which theorem? Slivniak's theorem?
Yeah, Slivniak.
Yeah, Slivniak's theorem is concerning a very specific probability measure called the palm measure. So what it means is, so until now we have talked about like a point pattern.
It is a bounded problem. If it is a bounded problem,
it's not actually bounded. It is more to do with conditioning.
Condition.
Okay. So what we are saying is, condition that the process has put a point in this area. What is the distribution of point patterns in some other part of space?
Okay.
Correct. Okay. So condition that there is a base
condition
station.
Probabilities they might be used.
Yeah. So the conditional probabilities are actually kind of analyzed using what is called a palm reduced.
In most of the applications, we put it conditions only.
Condition only, right?
If so what happens, that will happen.
Yes. So the Slivniak's theorem is like a version of this applying this kind of using this conditional distribution for the case when the PPP under consideration is a Poisson point process. Okay.
Means it is like he has derived something like Poisson process, some condition on Poisson process?
Yes. Okay. So what he's saying is condition that the Poisson process has a certain point at a certain location. What is the statistical properties of such a process? Because once you condition that the process has a point at a certain location, so to take the lattice example, okay, it will become very clear. If I told you that the lattice has, let's say you take a square lattice, right? That means all the integer points are fixed, right? If I told you that the lattice has a point at 1, then you are guaranteed that the lattice has a point at 2, at 3, at 4 and all. Right? But for a Poisson process, because it's memorylessness, even if you know that there is a point at a certain location, it does not change the statistics of the other points, right? Yeah. Just like in the one dimension also is the same thing, right? Just because you know that a phone call has come now, doesn't tell you anything about how long it will take for the next phone call to come.
Yeah, that's true.
Right? So that property for a spatial case is generalized to Slivniak's theorem.
Yes.
Okay. So where it's being used here is she's actually fixing a particular base station and taking that base station and looking at the delay from that base station to its serving UAV and measuring the latency of that connection.
Okay.
And now she's taking every UAV connects to its nearest base station. And now we are asking what is the average latency across all the links, the left figure that you see here.
Okay.
Spatial average delay, right? That is what she's calculating. Okay.
Yeah, that I think his condition is good.
Yes.
So shall we, you tell us that it's almost like 5 minutes more to 5.
Yes.
You just tell me at 5 we'll close it?
Actually, that's what I wanted to ask Taiba. So Taiba, I think you have a lot of material, right?
Yeah. 60 slides are there. She is halfway.
Yes. So how do you want to do it? Because I think both these papers are available online.
Right.
Okay. This is published material. Okay. So I think this was in Globecom. The other is in ICASP. This year we are presenting it. Okay.
Congrats.
So we can actually, share the papers if they're interested, right? And the paper, anyway, we have discussed the slides, right? So my main request is to go and discuss the results, because now you're talking, you pose the problem, no? Now you talk about the results, and you kind of make sure that the next result for the ICAST result, you kind of build on it and say what is new. That way you can close it quickly.
Right.
So the other way I can put it like the code she has shared. So I'll ask them to work and come back, and if there is question, I think they can directly contact Taiba Sheikh for.
Yeah, but please put me in the loop so that
one afternoon or sometimes she gives half an hour. I can put a live session with them so that they can be answered.
Yeah. So maybe we can do one thing, right? So you can definitely do that. Okay.
Let's try to. She has shared the presentation slides. I'll pass it on to the participants.
Yes, yes.
And the codes also, what she shared, I'll just put it on to them.
Yeah.
Let them run it and see if they have any questions. I'll come back to you, sir.
Yes.
Yeah, that
that sounds like a good idea.
Yeah.
So Taiba, can you maybe spend maybe around 3-4 minutes for the results now, and maybe
Sure.
another 3-4 minutes. By 5-5, let's close it. What
Okay,
do you say,
sure.
Professor? What do you say, Professor Sai Prakash?
Yeah, that's fine, sir.
That's fine.
She
Let's
has
close
to,
it.
She has
Yeah,
some
yeah.
work to do, so I just want to make sure that it should not
Yes,
be
yes.
disturbed. But
Yeah,
otherwise the
no.
majority of portion she has covered. And
Yes, covered. The reason we wanted to give this example was
yeah, the
giving
results, if she keeps it, then we can spend few minutes and close it, sir.
Sorry?
If she presents some more results, if she wants, for 2-3 minutes, and then we can close it.
Okay, then why don't you go through the results quickly then?
Yeah, that's what.
That will make it faster, right?
Yeah.
Go for it.
So the first result is that, So this is the mean delay I was
Go to the
mentioning in the
plots.
first
Go to
slide.
the plots.
Okay.
We don't have time.
Okay.
Yeah.
Okay. Yes. So this is the mean delay I was mentioning in the first slide, the mean packet reception delay. The main takeaway here is that if you operate at a rate greater than some critical rate given by theta star, the mean delay will be infinite. So that is the first takeaway. The main background here is that if there are links, so many links with large distances, or if there are so many large links, then you are more likely to see a infinite mean delay. So that's a intuitive understanding of that. And this theta star, this threshold theta star, after which the mean delay is infinite, is purely a function of path loss exponent. It is not a function of base station density, or it is not a function of height of the UAV. It is purely a function of alpha. That is exactly why for any UAV height, once you cross this threshold, the mean delay is infinite. Similarly, for any lambda g.
Okay, next one.
So that's one thing. And and one more result is that with the increase in path loss exponent, we observed a decreased mean delay. The reason here is that as you increase your path loss exponent, as you operate in a higher denser regions, you see a reduced interference coming from the neighboring base stations because your alpha is very high. For that reason, the ratio S by I, the signal to interference ratio, would be very high, that it would cross theta. That is the reason why as you increase alpha, you see an unexpected decrease in the mean delay, and also associated with each alpha is a associated threshold theta, after which the mean delay is infinite. So this is one result in this paper. In the next work, what we have done was, instead of letting all the base stations talk to their UAVs, we had we have assumed a random selection protocol where where each base station is either transmitting or not transmitting with a probability p. So if PG is chosen to be some 0.5, only 50% of the base stations are active and the rest are all inactive. One straightaway advantage that you see is that interference will be reduced, right? Only 50% of the base stations are transmitting, so you see a decrease in the. So you might expect an increase in the mean delay, but there is another contradicting factor that would increase the mean delay. I'll discuss that here. So if we look at this slide, this PG corresponds to the probability with which the base station is active or not, and the x-axis is the theta transmission rate. You see, if and also this PG equal to 1 corresponds to our previous work that I have just presented. We have generalized it here to some arbitrary PG. So as you reduce PG, although there are fewer number of base stations that are active, the amount of time each base station takes to become active is also large. As in, if P is 0.1 or if P is 0.5, so 1 by 0.5 is the amount of time on an average that a base station should wait to get its turn to transmit it to its own UAV itself. So that is a delay in addition to the packet reception delay that we saw previously. For that reason, although a decrease in P, with a decrease in P, you would expect a decrease in interference and thus an increase in mean delay. That is not the trend. That is what we wanted to show here. And also, as you decrease P, you get to transmit it at higher and higher transmission rate. So that is one advantage, but at the cost of increased mean delay. All this yellow shaded region corresponds to the higher mean delay. Previously, when you were at P equal to 1, you had a threshold up to some minus 2 dB. But with decreasing P, you are able to transmit until if suppose you are at 0.2, you are allowed to transmit until 10 dB, but with an increased mean delay, which is again a win. And again, with increase here, this plot is mean delay versus theta for varying h. With increase in h, we see a decrease in mean delay. Sorry, with increase in h, we see an increase in the mean delay. That's because your average signal power drops. But we see a contradictory result in the A to G. The reason for that is that in the system model, we have assumed the nearest association policy for the UAV U, right? For the air to ground link, it is always possible that there is another UAV here, V, which is closer to this base station than U. Imagine there is a UAV here by notation V, whose notation is V. That nearby UAV may cause more and more interference at the X, thereby increasing the mean delay. That is one reason why as you increase H, as you decrease H, the nearest interferer is closer to X, causing increased mean delay. Whereas in the G2A case, that is not the case. As you increase H, you will see a decrease in the mean delay. So you see these contradicting results. These contradicting results will ask you to design the network carefully, considering the base station density and the height of the UAV. And then the result here is for A to G, and PA is the probability with which a UAV is picked or not. The same result follows here. And one important point that I want to mention here is in G2A, this A of PG comma theta, or else the set of points for which the mean delay is finite, is independent of lambda G and lambda A. But here in A to G, it is a function of lambda G and lambda A. As in, if you have more and more, or else if you have more lambda G, since eta is lambda A by lambda G, you will get a lambda G in the numerator. As you have more lambda G, you will have more and more choices of P and theta for finite mean delay. But this would affect the G2A in an opposite way. Why? If lambda G is more, the interference on the from the ground is more on the G2A link. So this suggests you that you cannot arbitrarily choose any values of theta, PA, lambda G, and lambda A. There needs to be a careful selection of all these parameters. And this careful selection is given by this mathematical model, this way of deriving conditions on the finite mean delay. So that's the takeaway.
Okay, great. I think that is it. So basically what we are saying is you cannot have arbitrary sort of, because the geometry. Yes, exactly. So the big picture here is how do you design, when you want to design a UAV swarm talking to a set of terrestrial base stations, how should the channel access schemes be designed? How should the size of packets be designed for low latency communication?
Yeah.
Okay, so that is the one line sort of a problem statement, right?
Yeah.
All this analysis is basically to reduce those things into more mathematically tractable analysis.
Yes, sir.
Okay, so all of this can be cast like that. Okay, so yeah, so I think that's about it. So I hope we have not sort of gone too much over time.
Yeah,
I really thank Professor Sai Prakash Garu for giving us this opportunity.
I have to thank you, sir.
Yes,
I thank Ms. Tayaba Sheikh and Professor Sundar.
Yeah.
Because actually I know that I was there is a fasting going on, and I was actually planning in the morning, but the power cut has
No problem. No problem.
spoiled
Yeah,
it.
yeah.
And even afternoon also there is a small power cut and it has delayed.
No
Thank you,
problem.
ma'am. Thank you for
no,
the
I think
nice
I
invitation.
think this is part of something we cannot control.
Yeah,
So
yeah,
I think
yeah.
we should
Yeah.
just let it go.
So,
Right?
I'll ask the participants, I'll pass on the codes and ask them to go through
Yes,
it. And in
yes,
case
yes.
of problem, I'll put it back, email to Ms. Taiba
Yes,
for
yes,
that
yes.
clarifications.
Yes. So
Thank
Taiba, I think my one suggestion that I have is,
Yeah, sure.
Yeah.
why don't you put all these codes in a Google Drive?
Yeah,
Yeah.
we are putting it, sir. No,
You
she
put
has
it in
shared
Google Drive?
already, she has given the codes to me.
Okay,
She has
I'm asking you
sent
to
a
put
mail.
in Google Drive and give it to you so that it's accessible to anybody who wants to. Do it.
Right. We can just share the link. Yeah.
Actually, she
Yes.
has given the zip file to me.
Google Drive is better, no?
Yeah, okay, sir. Okay, sir, that is fine.
Then, yeah,
Because
no,
the
no,
Google
it's for you
Drive,
also
the
it will be better.
participants will not get access. I will get access, sir.
Oh, I see.
Yeah. So,
Okay.
But
Yeah,
anyhow,
yeah.
sir,
Thanks
once
a lot.
again, thank you
Yeah,
very
yeah.
much, sir, for
This is good, yeah.
actually
Yeah.
accepting
You're
the
welcome.
invitation and giving a nice lecture. And I also thanks Ms. Tayaba for
Thank you, sir.
participating on the demos and some knowledgeable programming part.
Thank you.
Thank you, sir. Thank you very much, sir.
Yeah, thank you very much. If there's any questions, please feel free to reach
Yeah,
out to
sure,
us,
sir.
okay?
I'll put it back
Yeah,
to you.
thank
Sir.
you.
Thank you, sir.
Yeah, thank you. Bye-bye.
Any
Yeah.
questions? You want to ask any questions? No, thank you. Sir. Sir, one more question, sir.
Yeah, please.
Yeah. So you want a process, what is the process followed for the data packet transfers from ground to air and air to ground? So
Process means?
as I understood, it's a random process, but anyhow, professor will speak about it.
What is the...
So they want how the packets have been transferred from ground to air and air to ground. Is there any access mechanisms you are trying to use?
Yes, good question.
Yeah.
So the way, what we assume is, if you open any data sheet corresponding to a modem, okay, you will have what are called waterfall curves. Are you familiar with this concept of waterfall curves? Basically SNR versus packet error rate. Okay, so what any modem does is, it will tell you, if you give me this much SNR, I can give you this much of frame error rate. Correct. So what we do is, we model that by having a situation where if the SNR exceeds a certain threshold, then the packet is received successfully. So it doesn't matter what specific modulation, whether you're using OFDM, it really does not matter. Okay. You can use OFDM, you can use OTFS, you can use MIMO, you can use some single carrier, doesn't matter really. So what we are doing is, we have simply assumed that you have a threshold behavior in terms of receiving the packet or not receiving the packet. The threshold is controlled by the theta, which is a SNR threshold. That theta is related to the size of the packet. Okay. So if the packet size is large, theta is large. If the packet size is small, theta is small. That is intuitive, correct? Right? So if I want to send a large packet, I need to have very good SNR, because anywhere the packet has a problem, that entire packet is lost, right? So that is the model that we are using, okay? Now, so that kind of, if you go back and look at our paper, we talk about basically a packet size which is given by log 1 plus theta. So you may ask, where is this log 1 plus theta coming? That is coming from Shannon's formula.
Yeah.
Okay. So that is, to put it in a nutshell, that is how we are assuming the transmission. And this is very commonly used, in most cases, even when you want to design something. Because you cannot assume every small thing about the modulation. So you assume something close to Shannon and you put a margin on that. Let us say you are 10 dB worse than Shannon, right? Then you will still have log 1 plus SNR, but then SNR is 10 dB worse than what Shannon will give you. Okay? Any questions? I hope it's clear.
So I hope you understand that the theta value tells you whether the packet has to go for retransmission or it will be received properly. That's what sir was trying to express. Is there any other question? No? Okay, sir. Thank you, sir. Thank you.
Yeah,
And
thank you so much.
We'll close the session, sir.
Yes. Thank you.
Sir.
Bye-bye.
Thank you.
Yeah.
Thank you, sir.